Okay, so let's now start solving the exercises of this section. The first one, actually we do not have to do anything. It asks us to prove lemma 11.8.4, which was that lemma which tells us that just like ordinary length, alpha length is also additive. And while going through the section, we have already indicated how to do so. So this one is done for us. In the next one, we have to state and prove a version of proposition 11 to 13 for Riemann-Stieltjes integral. The original proposition was this. Suppose f is a piecewise constant function on the bounded interval I, and f is piecewise constant with respect to two partitions P and P prime of I. Then the PC integral of f with respect to the partition P is the same as its PC integral with respect to P prime. This was proposition 11 to 13. And now we have to first of all state its Riemann-Stieltjes integral version and then prove it. So let's start the solution. So now we are going to need, besides f and these partitions, that function alpha as well. You can start the solution by writing something, in the beginning, that the following is the Riemann-Stieltjes integral version of proposition this. I'm not going to write that. I'm just going to write the statement itself. Let I closure be a subset of X where X is a subset of R, where I is a bounded interval. Okay, so I is some bounded interval whose closure is contained in a set X, which itself is a subset of R. Let alpha from X to R and f from I to R be functions where f is piecewise constant PC with respect to two partitions. P and P prime of I. Then the PC Riemann-Stieltjes integral of f with respect to P is equal to that integral with respect to P prime. For this statement, we do not need alpha to be monotonically increasing, not yet. Okay. Still it's going to be true. Just like proposition 11.8.4, that alpha length is additive, there also we do not need alpha to be monotonically increasing. Okay, now how can we prove this? You do not have to do anything much to prove this. You just make these changes to the previous proof, to the proof of the old proposition, these changes. To prove this, replace every length with alpha length and something else also needs to be changed. Theorem eleven 113 with lemma eleven 84. Yes. But where do we have to make these changes? In the solution, to exercise 11.2.3. This is where in this solution, when solving this exercise, we proved the old proposition. So you go back to that solution and there you make these changes. Wherever you see length, replace that with alpha length, and you will also see that in the old proof, theorem 11.113 has been used. In its place, now you have to use lemma 11.84. That's all. That will give you the proof of this. So this is the solution. Let us now see the next one. The third one next. This one is also similar. State and prove a version of this time theorem (11 to 16) for the Riemann-Stieltjes integral. So the original theorem 11 to 16, it tells us about the basic properties of PC integrals. It's that thing. So let me straight away write the statement itself. So here we are going to need, besides I, x and those things, alpha of course, but also two functions f and g which are piecewise constant. So let me start like this. Let like that I closure be a subset of x and x be a subset of R, where I is a bounded interval. Unlike the previous one, here we will need alpha to be monotonically increasing. Otherwise, one of the claims is going to fall apart, it won't be true. And it is that claim which tells us that if our function, besides being piecewise constant, is non-negative, then the Riemann-Stieltjes integral is also a non-negative real number. That won't be true necessarily if our alpha is not monotonically increasing. Alright, let alpha from x to R f from I to R and g from I to R be functions where now we impose the restrictions where alpha is monotonically increasing and f and g are piecewise constant on I. With respect to some partitions, okay, we do not have to worry about partitions anymore because by the previous result, no matter which partition we choose, we end up getting the same integral. Then, okay, so now we write the parts. Part A, we have the PC integral of f plus g, but do not forget PC Riemann-Stieltjes integral, so that d alpha will be there over the interval I is equal to PC integral of f over I plus PC integral of g over I. So this was the first one, that is sum, and then the other one which naturally comes after this, where we multiply one of the functions, say f, by a real number, by a constant. Part B, for any real number c, the PC integral of Cf with respect to alpha is c times the p. Okay, this you understand, this is product. Okay, c times PC integral. It looks a little confusing. C looks like a part of this abbreviation PC, but you of course know C is a number. These two identities or these two rules together say that integration is linear, that these make up the linearity property of integrals. Then parts, let me write C there on that side. Because we have PC functions now, so integrability is not an issue. Just like ordinary Riemann integral, PC functions are always Riemann integrable, but general bounded functions may not be. We have already seen one example. Then what is part C? Oh, okay. In part C we have the difference of f and g. Which is a consequence of parts A and B. F minus g, this is PC integral of f minus PC integral of g. Then part D. For this part D, we need the condition that alpha is monotonically increasing, because this is going to tell us about non-negativity of integral. If f of x is non-negative for all x in I, then this is also a non-negative real number. And now if one uses this and this parts C and D, then one gets a similar thing for the two functions f and g. If f dominates g, then the integral of f is also at least the integral of g, that is, it's greater than or equal to the integral of g. And by domination I of course mean this: if f of x is greater than or equal to g of x for all x in I, then this is greater than or equal to the PC integral of g. That thing. It's a straightforward application of this one and this one. You can immediately see. Next, part f. In part f, we extend the function. Oh, but before that there was another one. No, I think I forgot to write that. Yeah, before that there was another one. What happens if the function f is constant actually? If f of x is equal to c for all x belonging to I, where c is a constant real number. Constant, we write constant to emphasize the fact that c does not change with x. Then this equals c times the alpha length of I. In case of Riemann integral, we just had c times the length of I. Here we have alpha length of I. Then g. Yeah, in g now we extend the function f. Let I be contained in another interval j, which is contained in its closure, of course, that's known, but the closure itself is contained in x, and x is our original function, original set x, and this is a subset of R, where, but we need to also mention, j is a bounded interval. Okay, now define a new function f from j into R by this rule. Capital F is just small f if x belongs to I, and 0 if x does not belong to I but belongs to j, of course, that's understood. Then capital F is just like f, capital F is also piecewise constant on j. Small f is piecewise constant on I, this one is piecewise constant on j, and the PC integral of capital F with respect to alpha over j is equal to the PC integral of small x with respect to alpha over I. And then there is one more part where we partition the original interval I into two parts. So this one is going to be part H. If j comma k, this j is not that j, okay. This is in fact a part of I. That j was such that I was a part of it. This is a partition of I. Then the restrictions of F to j and to k are piecewise constant on their respective domains, and the PC integral of f with respect to alpha over I is equal to the PC integral of the restriction of f to j with respect to alpha over j plus the PC integral of f restricted to k with respect to alpha over k. This is the statement of that result, but now for Riemann-Stieltjes integral. Now how can you prove this? Do not be afraid, we do not have to do here also anything much. In fact, it's rather easy, very easy. I think replacing every mention of length in that old proof by alpha length is enough. Yes. To prove this, replace length. Every length you understand with alpha length in the solution to which exercise? 11 to 4. So in this exercise actually we proved the old theorem, old proposition, whatever it is. What was it? Theorem, I think. Yes, theorem. And that's it. If you are not convinced, I urge you to really do this. You go back to the old proof and there you make these replacements and see if it makes sense. I have already seen this carefully, but you also see if you really want to be absolutely convinced that yes, what I am saying is really true. Or you can just simply assume that this is true. This is something that you just have to see once. It's also not anything really very complicated or anything. You just have to see that, okay, the steps are okay, the logic is okay, so we have the proof. There are a few other exercises also in this section, but that we will solve next Sunday. And tomorrow again we have, what do we have? We already did number theory, I think, last Monday. So tomorrow let's go back to trigonometry again. And what do we do there? We have already completed the section, so we now have to go to miscellaneous examples. And then after that, miscellaneous exercises. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.